The topic today is deep learning and open data in molecular informatics, and this is going to be a very personal selection and by no means a complete overview about the topic. In fact, it's going to be very focused. What I completely ignored during most of my personal history in cheminformatics was the whole area of pharmaceutical cheminformatics, which is an area which, of course, actually keeps the field alive and is occupying and entertaining most of the conferences that we go to in cheminformatics. So that is, for example, one area that is not going to be touched today. Since this is the 50th Stammtisch for NFDI for Chem, I thought I realized I'm also looking back at now 30 years almost precisely of a personal history in cheminformatics. I think Sonja just mentioned it in her talk, and I thought I go back to my PhD thesis in Eberhard Breitmeyer's group. This is me in my doctoral card many years ago. And this is the outcome of my PhD thesis, which was actually half natural product chemistry and half it was already cheminformatics, the first project that I ever wrote. Lucy, most people here in the audience will hopefully not know Visual Basic anymore. So this is a Visual Basic user interface, and there is a DLL, a C program in the background. And what Lucy did, it took input data from NMR spectroscopy about natural products, and it used that to mostly the 2D information. It used that to deduce the chemical structure of the unknown compound. I gave a few candidate structures. And in fact, that was the first time that I realized that we are not in a very good situation in terms of open data in chemistry. For this type of exercise, you need a lot of training data. And ideally, if you have, like in this case, more than one solution in the end, it would be great to be able, for example, to predict an NMR spectrum and do some kind of ranking of your solution structures. And in those days, there simply wasn't anything available. I sold this program to Bruker, which put it in a drawer, and that was it. And over the time, I think this was the starting point of a journey through open data, open science, open source, which has shaped most of my scientific life afterwards. Some of you, or quite a number of you, have accompanied me on that journey. With Egon, for example, in 2000, we started the chemistry development kit, the CDK. And over the years, I was working on many open databases, many of them listed here. Open infrastructures like Phenomenal, for example, which was a European project. And the journey is not yet over. We are still working on many of these projects. And in fact, I'm particularly proud of NMR ShiftDB, which was DFG funded a long time ago, which is still alive thanks to the great work of Stefan Kuhn, who was a postdoc in my lab these days. The first open NMR database, in fact, which also was part of the funding capital, if you wish, of NFDI for Chem. And we are now working on NM Archive as a successor. But what I actually want to talk about is the importance of open and of big data for what we currently see as the global artificial intelligence revolution. And again, I would like to start with my personal eureka moment in this global AI revolution, which was in 2016, in an event which was, at least at first sight, not related to chemistry at all. And it was a tournament where an AI developed by DeepMind, which is now owned by Google, called AlphaGo, was supposed to play against Lee Sedol, the top-ranked player of the game of Go. You see Lee Sedol here in the forefront and a Go board here at the bottom. Go was, in these days, supposed to be one of the last areas of a complex game which was not solvable by AI or solvable by computing power. And in fact, as you all know, many years ago already, the first computer won against Garry Kasparov, developed by IBM. So that the problem of chess playing was solved a long time ago, but Go was different. Go is a game played on a 19 by 19 board, as shown here. And there are black and white stones. Each player puts a stone on the board. And in the end, the stones surround black territories and they surround white territories. And the one with more territory wins. And in fact, there are more valid board positions on a Go board than there are atoms in the known universe. And that makes it impossible to solve by combinatorial problems. DeepMind developed a complex set of algorithms, a Monte Carlo search engine backed by some other neural networks that were supposed to do the ranking. And in fact, they completely surprisingly won the tournament against Lee Sedol. Lee Sedol won one game and AlphaGo won all the others. And that shocked the whole world, at least in the Go area. And it kicked off one thing in me, which was a realization that I'm going to talk about later about the amount of data that is needed for playing and training these deep neural networks. Yeah. In this tournament here, DeepMind's AlphaGo used over 1,000 CPUs and 176 graphical processing units. That was an immense compute power that was needed in these days to run this neural network. Here, by the way, is the DeepMind engine room during the game, where they were watching all these exciting moves going on and judging. And here in the forefront, you see Demis Hassabis, who, of course, you all know, won the Nobel Prize in Chemistry 2024. And these days, he was head of DeepMind, and he was interested in solving this problem of playing Go. Yeah. A few days almost, days, weeks, maybe months after this tournament, DeepMind published AlphaGo Zero, which was a complete rewrite of this whole engine. And the interesting part about AlphaGo Zero was that it started from scratch by knowing almost nothing about Go, only knowing the rules, how to place stones on the board and how to evaluate a position on the board. And then they had two instances of AlphaGo Zero playing against each other. And while they did this, they got better and better and learned more and more about Go. After 24 hours, AlphaGo Zero playing against each other discovered 3,000 years of Go theory, surpassed the playing strengths of the previous engine, and surpassed the playing strengths of everybody on the planet. Yeah. And shortly after, it developed superhuman playing strength. And this was on a single machine in the Google Cloud with just 4 tensor processing units. Yeah. So enormous development after a short period of time. And this was actually the central eureka moment. You can see here that in 2016, deep neural networks, these were transformers and Monte Carlo engines behind them, were able to develop in a well-defined area, on a well-defined problem, to develop superhuman capabilities if they had enough training data. And of course, playing against each other gives you essentially endless amount of training data. And that is, of course, a situation that we in chemistry have almost in no area at all, as you all know. And one of the reasons is the disastrous way in which we do data management, but that's a different topic that I'm not going to pound upon today. Today we are celebrating. You all know that there is another area which is currently revolutionizing the way we live on this planet, and maybe is going to change the way mankind lives or doesn't live. Yeah, who knows? Fundamentally in the near future, which is the large language models, which are basically working, or they are benefiting from the same principle, which is they have at their fingertips all human knowledge that has ever been published. And as you know, they are now currently solving an enormously wide range of problems for us, which we don't have to do ourselves anymore. This is a time charge starting before the 2020s with the first GPTs by OpenAI. And the chart shows the amount of hours that modern AIs can work on a particular software task to complete the task in 50% of the time. And we are now, I somehow have to get rid of this speakers window here from my presentation. We are now at almost half a day that these and that's getting longer and longer at high speed, that these AIs can work on their own on a specific problem, get the task done after a certain amount of time. We are now already further. Just yesterday, GPT 5.55 was released. Claude Opus 4.7 is solving software tasks at an unprecedented quality. So it's we are seeing an amazing development, and I guess in our group and in many other areas, we are at the situation that we are virtually not writing code anymore. So it's mostly well-specified problem descriptions, and the AI is writing the code. So the bottom line in all of this is deep neural networks can develop superhuman capabilities if they are presented with a well-defined problem and a lot of training data. That's the kind of insight. And one of the questions, of course, is where in chemistry are we facing this situation? The answer is basically nowhere. But of course, we have been using, big data or large data sets. Let's call it like the definition of big data is always difficult. We have been using big data in many application scenarios. I already mentioned my lifetime scientific toy project, computer-assisted structure elucidation, where prediction of spectra is an important application. And for the prediction of spectra, you need training data in order to train neural networks, and you need structure generators like the one that I see Aziz is here. Hello, Aziz. That Aziz has been developing in his PhD. And I also see Michael Wenkes here, who is mentioned here with Sherlock. So these are areas where a lot of data really, where the applications benefit from a lot of data. The training of neural networks for shift prediction or using host cores or anything, they all need large data sets, and the bigger, the better. Yeah. So host code prediction, for example, is one area. Another area that we have been interested in, and this particular application was developed by Peter Oertel at Novartis, was predicting the likelihood that a particular given structure is a natural product or not. For this, again, you are benefiting from large data sets of natural products like the one that we are developing, coconut. I'm going to mention that later in this talk. And another area here is something that Jonas Schaub, who is also here, is working on in my group, prediction of certain properties of natural product structures, predicting scaffolds, predicting the most frequent scaffolds in large data sets based again on data sets like coconut, and so on and so forth. So all of these developments have in common that we need large collections of experimental and structural data to do machine learning training, to perform statistical analyses. It doesn't always have to be machine learning, and to distill scientific principles in the end that we are interested in. Yet, if you look at the data sets that we have available, you have to ask yourself how big is the biggest data set that we could actually have access to. And well, we all know PubChem is probably the largest database that we have, but PubChem is essentially a collection of chemical structures. Typically, when we want to train machine learning techniques like NMR data, we need chemical structures, and we need, in addition to that, physicochemical properties of these structures, which are hopefully and ideally measured and carefully curated. And if you look at such data sets, the landscape becomes extremely small and extremely scarce. NMR ShiftDB, for example, for the training of NMR data, has around 50,000 structures and associated spectra. That's virtually nothing. The biggest chemical database that you could call big data, I think, in my opinion, would be Campbell, with a dedicated scope on biological activity. You have small molecule drugs and their measured activities. And there we are looking at some 6 million structures and their data points. we are nowhere in the order of a few 100 million or anything near to the amount of data that, for example, DeepMind has been able to use for training their Go engine. A huge success story that we all know, and I already mentioned Demis Hassabis winning the Nobel Prize for this, was AlphaFold. That's biochemistry, it's structural biochemistry. And it's a beautiful example of what we could solve these days in chemistry if we had enough data in most of our research areas. AlphaFold is able to do a prediction of three-dimensional structures of proteins based on the amino acid sequence. And this wonderful achievement was possible because the protein structure community had been collecting structures of proteins determined by X-ray and NMR since, in fact, if you look back to the PDB when it started, since the 70s. That's an amazing time range, 55 years. We are anywhere close to that in other areas of chemistry, but it shows how successful open data can be if you have enough of it and if you start early to collect it. But so how do we get to big data in chemistry? I'm a natural product chemist, so that's why I'm always referring to natural products in this talk. But of course, that holds for basically any other area in chemistry. And the solution to the question, or one of the answers to the question here, is actually now bringing me to an application area where we as a group had a fun project, and where we as a group realized that we actually had one area at our fingertips where we had almost infinite training data, and that was the extraction of data from the chemical literature, and then after extraction, putting it into open access databases. This is a way of working that the chemical information industry with chemical abstract services at the forefront has been dealing with for many, many decades. Scientists publish papers, they publish information in papers. We all know we are destroying information in the way we publish it in papers. And so somehow you have to get out of the information out again. Some way of doing this is human curators. And then you have to have a lot of money like CAS has to pay all these many hundred curators, or you try to do it automatically. And that was one of the areas that we tried to attack, and we are still working on this. And I would like to show you what role big data plays in this project here. This is a typical picture from a Journal of Natural Product papers. There is an abstract with some information, and there are these typical 2D drawings of chemical structures. In the abstract, you find things that are interesting for databases: in which species has the compound been found, what is the chemical class, the chemical name, what is the biological activity. That is something that maybe the chemical database would be interested in. And now you have to get the information out again. The human curator now sits down, takes a chemical editor like ChemDraw or Catcher, and redraws all these structures. I've been leading the CHEBI database at the European Bioinformatics Institute for 10 years. And we had a group of 5 curators who did nothing else the whole day. Sitting down, redrawing structures by hand, checking it carefully, getting the names out, and creating another dataset or database entry for CHEBI. And that, of course, is something that a long time ago I had the numbers, how many datasets can a human curator curate per year. That's not really many. So that is not sustainable to get data at a scale that we are interested in. For a machine, this problem is not so easy, because if you zoom in, you will see that these are not vector images and these are not machine readable structures. It's essentially black and white, or it's grayscale pixels on white background. And somehow you have to translate that back into a machine readable structure. And that was actually, in fact, one of the biggest toy or fun projects that we engaged in the last years. Kohulan, who worked on this, is also in the audience today. So greetings to you. The problem itself is you start with a set of black and white pixels on paper. You employ a program for so-called optical chemical structure recognition, and out comes a machine-readable format again, a SMILES or a MOL file. And we have been working on this for a long time, but so have other people. The traditional approaches is that you use rule-based methods. You scan the structure, you do vectorization, and then you run a number of heuristics and algorithms on the data and then eventually you come up with a chemical graph that you can retranslate into a MOL file. This is a very error-prone process, as those who worked with these old tools know. And we thought we could actually maybe do it a little bit better. So the system that Kohulan developed is called Decimer, and the big insight behind Decimer is that we can actually develop the training data ourselves by artificially generating 2D depictions based on large data sets, like PubChem, for example, which gives us millions and millions of images which we can generate. And then we can present the data, the image, and the corresponding SMILES, because we know it's artificially generated training data, to a modern deep neural network like EfficientNet plus a transformer. And over time, if you only present enough of these examples to transformer, the transformer learns how to translate an image of black and white pixels to a SMILES. And there is nothing else, no underlying assumption is given to the model. It's a generic deep learning model, which is presented with an image and the SMILES and many, many examples. And then it learns over time the complete chemistry. And that was a completely stunning insight. Now, one of the key solutions in getting this really to work very robustly was actually developed by a PhD student in my group, Otto Brinkhaus, and it's called RanDepict. And what RanDepict does is it takes each of these input image examples and it generates, forgive me for that, it generates all the bullshit that humans do when they publish chemical structures in papers. We use poor resolution, we use semi 3D images, we put images to depict HMPC signals, not images, arrows into structures. We put atom numbers onto them, and all of them makes it extremely complicated for deep neural networks to understand these images properly. But RanDepict generates all of these so-called complications, yeah. And if you present enough examples with these complications to the deep neural network, it learns to ignore all the bullshit, like the arrows and the numbers, and only focuses on the chemistry in the image. And that was actually, I think, the breakthrough for the Decimer system to make it so robust. So Decimer these days. I don't dare to do a live demo. Decimer lives at decimer.ai. The whole system has been, do I have the citation? No, of course not. The whole system has been published in Nature Communications, and you can test it. You can take your PDF. You can go to decimer.ai, upload it, and get a structure out. Kohulan at one of the last German conferences on chem informatics also did a nice test. He photographed the slide with the structure during a talk and uploaded the photo to Decimer, and Decimer was able to translate the structure on the slide from the photo into a machine readable representation. So that shows how robust the whole system really is. We continued the work by combining Decimer with information extraction using large language models from text, because of course the structures is only one part of the story. The system to integrate all of this is called Marcus, in honor of Marcus Ennis, who is the longest working curator of the CAPI database. And Marcus allows you to upload a journal article like this one here. It extracts the text it finds all the relevant keywords and extracts them. It then runs the structure recognition using actually 3 different models. So here we have something that I think these days is called a group of experts. And each of the 3 systems for structure extraction does the job. And then you can compare what the different systems are actually doing. And either they agree, or if they don't agree, you choose the one that you have the highest trust to. And then that allows you then to submit data sets to Coconut, for example, to our natural products database, or later, if we continue to work on this whole system, maybe to NM archive and other data sets. Now, clearly, as you all know, and here I'm coming to the end of my talk, and I'm doing the U-turn again to NFDI for Chem. Getting destroyed data out of the literature is we should only go this way if there is no other possibility. As you know, that most of the scientific, technological developments on this planet are on exponential growth curves, and also science today is publishing more data in a given year than has been published, let's say, in the 50s in 10 years. So it's definitely worthwhile to look into the future and to think about that a much more sensible way is to let scientists submit the data directly to scientific repositories. And that is one of the areas that, of course, NFDI for Chem is championing the whole scene. I would like to finish by talking about 2 databases that we have been working on in the NFDI for Chem context, which is the first one is the Coconut database, which currently is the largest database of natural product structures on the planet, lives at coconut.naturalproducts.net, and has recently been completely refurbished. We have about 700,000 unique molecules in the database, annotated with informations about the organisms they have been found in, the geolocations that they have been found in, of course, all the articles where these have been cited. Now, if you compare the numbers here, 700,000 molecules in Coconut, but only 200,000 with organisms attached to them, and only 100,000 with citations, that means provenance, articles in which they have been cited, you see that there is a huge data quality problem in the database. And this is because it's a database accumulated from historical data, which have been lying around in other databases. And I don't think we can ever fix this problem anymore, because it's virtually impossible because of the situation in the chemical publishing landscape to close all these gaps. It would essentially mean that we have to use AI or robots and go into all the libraries on the planet. A lot of these have been published in Asian journals, in Chinese and other languages, which are for us hard to access, and go through all the printed materials and get the information out again. As you can probably imagine, that is close to impossible. In the interest of time, I'm jumping over the details here. If you're interested in natural product chemistry, you will know Coconut. And I would like to finish with showing NM archive, which is my big hope in solving one of the problems that I'm most interested in, which is a reliable prediction of NMR structure for structure elucidation. Other than, or in contrast to NMR ShiftDB, NM archive really holds the original NMR data that people are depositing, and that will allow us to do the training of neural networks for NMR prediction in an unprecedented quality. And with this, I'm jumping over all the rest here and come to the acknowledgements. I would like to thank my wonderful team that's been supporting me over the years. All the colleagues from NFDI for Chem, obviously my dear collaborator Achim, who has been instrumental in driving Decimur forward. And something that I would really like to mention here without making too much advertisement is Google, really, who was the company who enabled us to do the Decimer project. In order to train such a deep neural network with that many training data, doing it on a 20,000 euro graphical processing unit, a Tesla V100, would have taken 6 months, one training. And if you consider that a PhD thesis is 3 years, maybe, then you know that a PhD student has like 6 tries to get the training right. And you can probably imagine that this is nothing that would work. Google gave us access to their tensor processing units in the research cloud, which brought the 6 months training down to a few days. And that enabled us to actually do the training in a successful way. And with this, I'm finishing. I thank you very much for the opportunity to show this work and for your kind attention.